All right, so what we're doing here is we're kind of reviewing the four methods of solving exponential or log equations through this foldable. This one is supposed to be kind of like a four windows kind of thing, so you're going to turn your paper sideways and fold it almost to halfway so that you have like this section over here that can be like our titles. And after that, fold your paper in half twice so that we can have four sections. All right, so now you've got a title and then four window panes that we can summarize the steps for solving. All right, so I'll put this back up there, and this is where you guys pause and copy, and then unpause so we can talk about the examples that go on the inside. All right, so there are four basic methods for solving exponential or log functions. They're going to fall under these four different methods. So first, you kind of have to analyze what you're starting with. So if you have exponents on both sides, what we're going to try to do first is to see if I can rewrite each side to have the same base. So an example of that would be like these two. So I have over here a base of 4, over here I have a base of 1/2. Both of these can be rewritten as base 2. So if I rewrite this one with base 2, it becomes 2 squared, but I also have an x in the power. And this one is 2 to the negative 1, but I still have x minus 3 quantity as a power, so you can rewrite it like this. Since the bases are now the same, it means the powers must also be equal. So then I have 2x equals negative x plus 3, and then you simply solve for x at that point. Right, and then on this one, we have 1/3 as a base and 27 as a base. They can have a common base as base 3. So this one would be base 3 to the negative 1 power. There's already a 2x in the exponent, and this one becomes 3 raised to the 3rd power, and there's already an x minus 1 there. And again, since my bases are the same, that means my powers must equal. At the end of the video, I'll show you what all of these work out algebraically so you can check your work and make sure that you solved for x correctly. All right, so if you have exponents on each side of the equation and you can rewrite them in the same base, that's our first method. If you have exponents on each side but you cannot rewrite them to have the same base, then those problems would look more like examples 3 and 4. So here's my base 4, here's my base 11. Remember, this is 11 to the 1st power, so there is no common base that I can easily rewrite these as. So in these situations, since my bases cannot be rewritten to the same base, what we're going to do is take the log on each side. So do log base 10 of 4 to the x equals log base 10 of 11. And we have some properties for log that says the power is really a multiplier up front. So we can rewrite as x log of 4 equals log of 11. And now to isolate and solve for x, you divide by log 4. So you're going to divide by log 4. Divide by log 4. X equals log of 11 over log of 4. That's an exact answer, and then you guys can practice doing that in the calculator and give me a rounded answer. Okay, number 4 is similar. I have a base e here, and we're going to rearrange things. So first we're going to add 7, so 4 times e to the negative 0.3x power equals 20. I've almost isolated my base here, so now we need to divide both sides. All right, now when I get to this point when I'm checking out my bases, I can't rewrite e and 5 to some common base. So what we're going to do is take the log on each side. This one, though, since e is a special form of log, we're going to do natural log on each side. That way I can have a cancellation here. And so now I have negative 0.3 x equals the natural log of 5. And then I just need to divide by negative 0.3. So that's an exact answer, and then you can do an approximation in your calculator, and you can check your work at the end of the video. All right, so that's if my equations start off in exponential form. If you're not in exponential form and you're in log form, I'm going to first see if we can have our log bases be equal to each other, because if they are, then our arguments are equal to each other. So an example looks like this, where I have log base 5 of 4x minus 7 equals log base 5 of x plus 5. So since my log bases are the same, that means my arguments are equal to each other. And you can solve for x. If your log bases are not the same, or you only have log on one side, then the way you're going to want to solve this is by isolating the log and then rewriting it in exponential form. So that would be like this: log of 8x plus log of x minus 20 equals 3. So first we need to notice that we can consolidate this to one log using our log properties. And so if I'm adding two log functions and the arguments are really multiplying, so this is really like log of 8x times x minus 20. And we're going to have to distribute that. So now this is log of 8x squared minus 160 x. From there, to solve, since I only have log on one side of the equation, is we're going to rewrite in exponential form. This log is base 10, so when we rewrite it, it's 10 to the third power equals 8x squared minus 160x. From there, you're going to solve using the quadratic after you move over 10 cubed. All right, so coming back, you should have been able to use a quadratic formula or use the factoring method, and you come up with two answers since it's a quadratic. I get positive 25 or negative 5. With all log problems, since log has a restricted domain, there are certain values that x cannot take. So what you have to do is, after you get what you think is your solution, is you have to go back and substitute it into the arguments to make sure that you do not get negative values or 0, because that's not part of the domain for log functions. So when I substitute 25 in, I'm okay for both arguments because I don't end up with a negative value or 0. But when I substitute in negative 5 here or here, I get negative arguments. So that is a false or an extraneous solution. So your answer is just x equals 25 on that one. On this one, you should have got x equals 4. And when you substitute it in to the argument to check to make sure this is not an extraneous solution, we're fine. We still get positive arguments here, so we're good. And then on your exponent problems, these are your solutions that you should have. And you don't have to check for positive values for these, because on the exponential function, we can have any real number in for x. It doesn't have a restricted domain at all for those functions. So you don't have to check for extraneous solutions on the exponent equations.